Hi all, Minty Crab Nebula here. In this video I'll be deriving Tsiolkovsky's rocket equation. But first, a little background on Tsiolkovsky. Konstantin Edvardovich Tsiolkovsky was born in 1857 and died in 1935. He was a Russian scientist that independently derived the formula that applies to ideal rocket motion and proposed multi-stage rocket designs, among many other lifetime achievements. He can rightly be called the progenitor of the space industry. His vision, with his scientific work, definitely advanced space exploration, space experimentation, and humankind in general. Let us now begin with the simplest rocket scenario. So, a rocket is an object that uses jet propulsion to move through space. It can accelerate in either an atmosphere or a vacuum. Let us begin with the simplest case, where the rocket is fixed in position. This is done to test engine power, efficiencies, and so forth in aerospace engineering. So let us go further and say the rocket is a particle which sits in a certain position according to our inertial frame of reference. It should be said that we are only working with speeds that are much less than that of the speed of light. Using the concepts of classical mechanics is all that is needed here. So I'll draw a frame of reference. This is our abstracted rocket. And spits out a mass dm at some time, some velocity. Call that at origin, and that will be in the positive direction. Okay, there are two main types of propellants which are used in rocket engines: solid and liquid chemicals. In both forms, the chemical energy, which is really just the electrical energy, is released and converted to kinetic energy of the exhaust mass, and therefore per unit mass of the propellant we have. So where kappa is just some dimensional constant which depends on the units used, QR is a chemical energy reaction which is usually just measured in joules per kilogram of the chemical used, and V sub EX is of course the exhaust velocity. So that's per unit mass, so that's the kinetic energy. So we'll focus mainly on the exhaust mass in this example. The propellant inside the rocket remains at relative rest to our inertial coordinate system. When it is ignited, small units of mass dm are ejected at the back like said before. Thus each unit of mass has a momentum. P sub EX is equal to small unit of mass V sub EX. So looking at this impulse wise, the small unit of mass has gone from relative rest in our inertial system to a measurable velocity. This means there has been an impulse on that unit of mass. So we have the force times some small time period is equal to the change in impulse, which is equal to small unit of mass, the final velocity, take away the initial velocity, and of course the initial velocity is 0 in our inertial frame of reference, and we have, which we shall just call the same as up here, the momentum. So again, the initial velocity of the small mass is 0 at the initial time, since the rocket fuel is at relative rest to our coordinate system. By using Newton's third law, the force acting on the rocket by the gas is in the opposite direction of the rocket force which acts on the small unit of gas. So I'll just write the momentum, not the momentum, but the impulse up here. Call F rocket dt is equal to Vx, small unit of mass. We can rearrange that too by dividing by the dt. And that's equal to the negative force of the exhaust, which is just Newton's third law, because particle acts on the rocket acts on a particle in equal but opposite directions. So rocket to the particle is equal to the negative force of the particle to the rocket. And this is called thrust usually, and that's in the positive direction, because remember, if we're speaking of the rocket itself, this dm over dt, that is smaller than 0. That's a negative quantity because the mass of the rocket is decreasing. Typically the speed, or in other words the magnitude of the velocity of the exhaust of, say, a liquid oxygen and RP1 fuel mixture is around 2.5 kilometers per second, and that comprises mostly of CO2 and H2O molecules. So now let us move on to derive Tsiolkovsky's equation. For an ideal situation where the rocket is in free space, and which it can have no velocity or an initial velocity in reference to some inertial frame of reference. It is therefore not gravitationally bound or interacting with another system in any other way. For a complete abstraction, we can say that it is a particle in a system that decreases mass in a unit time period and changes its position only in one dimension. So if I set up a frame of reference here, I'll still draw the 3 dimensions. Actually, I might draw that a bit further over here. This will be the x-axis. Oops. Call that the z and the y. So this will be the frame of reference O, and I shall draw the rocket here at some initial time t, and at some later time right here, t plus dt, where it has spat out some small unit mass, not unit, just a small mass. So the whole rocket system is in reference to our inertial frame of reference origin, so we've called that O, which we are observing from. The propellant is ignited, therefore the rocket has less mass, dm, so we'll call that negative dm, and at some later time dt, which we have here. From our inertial frame of reference O, the rocket is moving in the positive direction. So with here, I might get the ruler out, and just do another, right, draw it like that. So it has some initial velocity, v. Let's call it v. And let's call that frame of reference r. And yeah, we'll call the rocket frame of reference r. And we observe the particle coming at the back of the rocket, because, well, from the rocket frame of reference r, the exhaust particle has a speed vex. So let's say from the rocket frame of reference here, when it spits out the back some mass dm, in the rocket frame of reference, we'll call that v exhaust r. And I'll draw a vector in there. And that's in the negative direction. The exhaust mass dm in our frame of reference has initial forward velocity, so from being in the rocket plus its new velocity away from the rocket. So it has an initial forward velocity v in our inertial frame of reference, plus the exhaust velocity in reference to the rocket frame of reference. So I'll just write that in like so. So in this case, in our frame of reference, it will be going forward like so. And we can write that, so the V exhaust of the rocket's mass, exhaust mass, from our frame of reference is equal to the initial velocity plus the velocity of the exhaust mass in the rocket's frame of reference. And the rocket itself, so the velocity of this particle, it could have either a positive or negative direction from the O reference frame. Because if you think about it, if the rocket has an incredibly high initial speed with a smaller exhaust speed, the net velocity of the exhaust gas dm from our frame O will be pointing in the positive direction. If the speed of the exhaust is much faster than the rocket speed, the net velocity vector will point in the negative direction, according to our inertial reference frame O. In the rocket frame of reference R, the exhaust molecule, or whatever, the small mass unit, will always be in the negative direction. If one sticks to the convention of the rocket going forward is in the positive direction. So we can rearrange this equation. So we can rearrange this equation here so that the exhaust velocity compared to the rocket's frame of reference is equal to Vex sub EXO minus the initial velocity. I should also say that in this small time period, the rocket itself has its initial velocity plus a new velocity dv, so some small velocity like so. And we'll say that's the rocket system there. I'll include that. Actually, I'll include all of that. And that's the initial rocket system there. So Next slide. So taking the snapshot at time t from our reference frame O, the rocket has an initial velocity and total mass m. So I'll just go that and put total mass m. And therefore its initial velocity at time t, initial momentum, is p initial times its initial mass times its initial velocity. It's self-evident. Now, so at a later time, which we have stated is some small interval t plus dt, the rocket has ejected that very small mass of negative dm, because it's losing mass, and the rocket system has moved forward by a small velocity dv, so we've said that small in that small time frame. So this means the rocket has a decreased mass, so its initial mass take away the small mass dm. So we can write this as m plus dm. So, oops. Like so. Therefore, the final momentum in this small time frame dt at the small time frame after t is the rocket losing its mass times its velocity plus its smaller change in velocity plus the mass that was ejected at the back, and that's all according to the exhaust in the O frame of reference which we are at. So we can then expand this plus mass dv, oh sorry, wrong, dm, what am I doing? Yeah, I had it right the first time, plus dm plus a negative dm vxo. Now, this term is an incredibly small quadratic term, so it can be just cancelled out because it's just really incredibly small. And we can rearrange the last two terms on this side, like so. And place dmvexo plus dm velocity, like so. And we can factor those out. So I'll go over here, factor those out. Factor the mass out. Like so. But that's just the same as saying of the exhaust velocity in reference to the rocket frame of reference. So we can write in there like so. So from now on I shall just denote the exhaust velocity with reference to the rocket. I'll just denote it as EX. save writing an extra letter. Now, from the conservation of momentum principle, we have dp, that's the change in the momentum, is equal to the momentum final take away the momentum initial, which will equal to some constant. So we'll have to equate that to the initial and the final momentum. I'll go to a new slide for that. So I'll just rewrite it. The change in momentum is equal to the final momentum take away the initial momentum, and that was, so the final momentum was that, so the mass times the velocity, the initial velocity, plus the mass dv minus the velocity with reference to the rocket take away the initial momentum. So of course they cancel out. We're left with like so. So we can divide by a small time frame. I'll put the velocity at the front of that term, and this equation is important, so I'll box that. So in this example, the rocket system is free. Therefore, from the conservation of momentum, the momentum must equal some constant. Therefore, this, I should really put that vector arrow up the top of that too, is equal to the force, which is equal to 0. Because of course, take derivative of a constant, it's just equal to 0. So this is a free system, and it's not interacting with any other. In my next example, I'll show you what to do when this is not the case, and shall modify this equation. So, rearranging this equation here, knowing that the force is equal to 0, the external force, we have now, since we are working in one dimension, it's clear that the exhaust velocity is in the negative x direction, and the thrust, which is this term here, is acting in the positive direction in our reference frame. So we can just put it in the scalar form and write it like this. Well, first I'll divide out the m, the mass, and multiply it by dt to rearrange it. But we can just get it in the scalar form like so. And like so. Now, take the initial mass m sub I and the velocity, the initial velocity v sub I, to be at some initial time t initial, which this is usually just set at 0. Then at some t time, final time t sub f, where the rocket has a final mass m sub f, and with this final velocity of v sub f. We also assume that the exhaust velocity is equal to some constant, which in general it is. So we can integrate with these initial conditions, initial and final conditions. So it's v initial to the v final of dv is equal to some constant of the exhaust speed, mass initial to the mass final, now this is just v final take away the velocity initial. Now that is just the natural logarithm of m of the initial mass to the final mass. So we can write it out like so. Take away natural logarithm of the initial mass. But using the log rule, so we have log c a take away some log c b is just equal to log c a over b. So here we can have, so I'll write this over here. So we can have Vx of ln, so the final mass over the initial mass. But we can go further, and because we can, using another log rule, so log c a over b is just equal to negative log b over a. So that we can then therefore write the equation like so. Mass initial over the mass final. Generally the initial mass is just 0 because you launch a rocket from the launch pad. So this is a general form, but if we take vi to be in 0, we get so this is Tsiolkovsky's rocket equation. Now, let's look how this equation is modified to take into account a constant gravitational field. I did that on the wrong slide. I'll just erase all that. I don't know why a line is appeared on there. Fault of the program. Alright, so I won't bother drawing the reference frame this one. Let's say the rocket is ready to launch on the Earth's surface, pointing straight up. Take the upwards direction to be positive x, and thus the gravitational acceleration will be in the negative x direction, and the exhaust movement will obviously be in the negative direction too. It should be noted that we can take some point on the Earth's surface to be approximately an inertial frame of reference origin, ignoring the small acceleration effects of the Earth's rotation, orbit, etc. We can also assume that the gravitational field remains constant for the distance travelled. In the last example, the rocket was away from any gravitational fields and thus has no external force acting on the system, so we wrote the change in the momentum was equal to 0. In this scenario, though, there is a clear external interaction of the rocket system. So there's external force acting on the rocket system, so we have to write in, going to this equation here, external force is equal to minus and that's a vector 2. So the Earth's gravitational field is interacting with the mass of the rocket, so the force external is equal to the mass of the initial rocket, the initial mass of the rocket, take away the gravitational acceleration, multiplied by the gravitational acceleration, So write that in there, you sub that in, now again, at this stage, since we're only working in one dimension, this is just for general three-dimensional space, what have you, we can write it as a scalar equation. So we know the gravitational acceleration is pointing in the negative direction in our frame of reference, and the thrust is in the positive direction, plus the exhaust speed over the change in the mass, the rocket's mass. So rearranging, we get the rocket's thrust is equal to no, shouldn't put that in there, just should put, I'll rearrange it like so, and I'll get rid of all this. So if we then divide by the mass and then times by a small time interval dt, we can get the following. So dv is equal to so this is Tsiolkovsky's equation in modified form. Well, when we take the integral, it's just much the same as last time. So the initial velocity, the final velocity of the small velocity, the rocket, that's constant. The initial time, the final time of some small time interval dt. So taking the integral, it's much the same as before, and so on and so forth. We get the final velocity is equal to the velocity initial plus the exhaust speed take away gravitational acceleration with the initial times the final time, take away the initial time. So this is Tsiolkovsky's equation for system in a gravitational field. Now, let us go to an example. So, the Russian Soyuz VFG rocket is the only rocket that is used currently to transport astronauts to the International Space Station. Its total mass before launch is 305,000 kilograms. The first stage burn time, where the core and the 4 boosters are ignited and burned, is 118 seconds from T0 and the launch pad. Assume the magnitude of the exhaust velocity relative to the rocket is 2.5 kilometers per second and is constant. Also assume that 198,000 kilograms of the fuel is consumed during the burn time. Right after this first stage, the 4 boosters are jettisoned. Calculate the speed of the Soyuz FG just as the boosters are jettisoned. So, we have the initial mass of the rocket to be 305,000 kilograms. With, after the T final, 118 seconds, it has a total mass, or it doesn't have a total mass, sorry. So the mass final is equal to its initial mass take away the mass consumed. So the fuel. So that will be 107,000 kilograms. And its initial velocity, of course, is 0 from the launch pad. And we'll take T initial to be 0. And the gravitational acceleration of the Earth is, of course, what am I doing? 9.8 meters per second squared. Okay. Now, using this equation here, which is Tsiolkovsky's equation for the constant gravitational field, we can calculate the final velocity. Let's write it out again. Mass initial, mass final, take away and we input the initial velocity to 0. I should also put constant speed, meters per second. So times ln, the natural logarithm of 305,000 kilograms over 107,000 kilograms, take away 9.8 meters per second squared times 118 seconds, and calculating that, calculator, we get meters per second, so 1,462.3 meters per second. So that's roughly 1.5 kilometers per second. It's moving very fast. So this is, of course, ignoring atmosphere, slight variations in thrust, and so on and so forth. And I'd just like to finish on, earlier on I said that one of the achievements of Tsiolkovsky was that he developed the theory of rockets with stages. So why are rockets such as the Soyuz designed this way? Well, basically, after the fuel and the boosters are consumed, the rocket is left with the extra mass it need not have. So the boosters are jettisoned, the mass is shed, and the rocket is now easier to accelerate with its remaining thrusters or boosters, whatever. Thus having an easier time reaching speeds needed for orbital positions around the Earth, or indeed to escape speeds to be able to escape the Earth's gravitational interaction. Where when we want to send spacecraft to other parts of the solar system or even beyond. So with that, I hope you found this video helpful, and thanks for watching.